Hi everyone, in this video, we'll start discussing data transformation. We'll cover three smaller topics: data normalization, encoding categorical variables into numerical ones, and dimensionality reduction. First, let's talk about data normalization. Before we dive into the definition of data normalization, let's look at a motivating example. In this example, we're predicting credit scores based on three features. Based on the descriptions of these features, we know that income ranges from $30,000 to $100,000, monthly credit card spending ranges from $200 to $5,000, and the number of loans ranges from 0 to 5. Based on these feature descriptions, do you notice any issues? Take a moment to think about it and see what insights you might come up with. In this dataset, the range of feature values varies dramatically. For example, within the income feature, the values fluctuate over a range of 70,000, while in another feature, number of loan defaults, the range is only 5. When comparing values between different features, the minimum income is 30,000, but the maximum for number of loan defaults is just 5. We call this phenomenon skewed data. Because of the way calculations work, these differences can cause the training process to overlook features that are represented by smaller numbers, which isn't the correct behavior. For example, in K&N that we learned earlier, we need to calculate Euclidean distance. In the calculation of Euclidean distance, we start by computing the difference between the values of the same feature into data samples. At that point, if one numerical value is much larger than the other, its difference will dominate, essentially diminishing the impact of the smaller numerical value. After we calculate the differences within a feature, we then need to compute the sum of the squares of those differences. At this point, if one feature's values are much smaller than another's, the squared values of the larger feature will dominate the calculation. In other words, the influence of the feature with smaller numerical values gets overshadowed. However, if we examine the original dataset, we see that it contains three features: bill amount, wait time, and tip. We can't arbitrarily conclude that bill amount plays a bigger role than the other two features. This is the main issue and challenge that comes with skewed data. The model might give too much priority to features with larger scales, like income, while overlooking other important features such as loan defaults. In the end, this imbalance can lead to biased predictions. Data normalization is used to address the issue of skewed data. Simply put, data normalization adjusts the numerical values in a dataset so they're all on a similar scale. It's common to scale the data to a range from 0 to 1 or from -1 to 1. The 0 to 1 range has the benefit of being small, so the numerical values end up closer together. On the other hand, the -1 to 1 range is symmetrical, which can help reveal patterns through its balance. Additionally, if the dataset contains negative numbers, the -1 to 1 range naturally accommodates them. Regarding why we need data normalization, this remains an open question. There isn't a single standard answer, but if you understand our earlier motivating example and the underlying logic, you should be able to answer this question fairly easily. Let's look at some common answers. First, data normalization adjusts all numerical values onto a similar scale, which ensures that the model treats all features fairly. As a result, when we make full use of every data point, our model is more likely to capture the overall trend, increasing its chances of performing well. Also, by utilizing every data point and each meaningful feature, the training process tends to be faster. Lastly, proper normalization enhances the interpretability of the machine learning task. As we've discussed before, many people refer to machine learning as a black box problem often. We know the model works well, but we can't explain why. A well-normalized dataset can help us gain more insights into how the model is making its predictions. Let's look at an example of data normalization. We have a dataset that contains the height and weight information for 5 students. You can see that the range of height values is much larger than that of weight values, which means the data is skewed. We should use data normalization to eliminate the negative impact of this skewed data. For a clearer understanding, I've plotted this graph to show how the data points are distributed in the feature space. You can see that the 5 data points are skewed toward the height feature, even though height and weight should carry equal weight. We can use this graph to revisit the issues that arise when data normalization isn't applied. Without normalization, we're treating the two features unfairly by inherently giving more importance to the height feature. As a result, the model will pick up more information from height during training. This biased weighting introduces misleading information and increases the difficulty of the machine learning task, because the model will have to work extra hard to overcome the negative influence of this initial imbalance. Now, let's look at a common method for data normalization, min-max scaling. Using min-max scaling, numerical values are rescaled to a fixed range, typically 0 to 1. The formula for min-max scaling isn't difficult to understand. We primarily rely on two parameters, the minimum value and the maximum value of the feature. In this example, we can easily calculate the minimum and maximum values for the height and weight features. This is the first step in min-max scaling. Next, we need to calculate how far each feature value is from the minimum value. Since we already know the minimum, we can simply scan through each data point and compute its distance from that minimum. In the third step, we calculate the range for each feature by subtracting the minimum value from the maximum value. This range is used as the denominator in the min-max scaling formula. Finally, we can calculate the min-max scaling results. In this example, you'll see that all the final numerical values fall within the range of 0 to 1. In other words, we have successfully transformed the original dataset into a new, normalized one through data normalization. Using the same method, we can plot the new dataset's data points in the feature space, and you'll see that weight and height are now treated fairly. Compared to the scatter plot of the original dataset, we can see that the new data distribution makes it easier to distinguish between different students. If this were a machine learning classification task, the new dataset would more quickly reveal clear patterns. However, there's a potential drawback with data normalization. It preserves the relationships between data points but discards the original numerical values. If our goal is simply to separate different data points, losing the original values might not be a big deal. But if the task involves predicting a specific numerical value like a person's height or income, then using a normalized dataset might cause problems. Of course, we can reverse the normalization process to convert the normalized values back into accurate numerical values. But doing so assumes that the new data point we're trying to predict falls within the range of the training set's minimum and maximum values. If it falls outside that range, then the original min and max values wouldn't be valid for converting the normalized value back. This is one of the limitations of data normalization. Now, let's learn another common data normalization technique, z-score normalization. Many people prefer to call this standardization since they refer to the z-score as the standard score. The z-score we're discussing here is the same one we mentioned earlier when talking about outliers. As you can see, the formula for calculating the z-score is exactly the same. Now, let's walk through how to use z-scores to normalize a dataset step by step. Step 1. Calculate the average value for each feature. This step isn't too complicated. In fact, on an exam, you might encounter similar calculations, so feel free to bring a calculator. Next, we need to calculate how far each data point is from the average value. The purpose of computing these centered values is to determine the variance for each feature. As shown on the slides, the variance calculation uses the centered data. We can calculate the variance using its formula and then take the square root of the variance to get the standard deviation for each feature. This standard deviation is used as the denominator in the z-score formula. Now that we have all the values needed to calculate the z-score, we simply perform a division and we get the z-score normalization results. You'll notice that the results include both negative and positive values. After z-score normalization, the numerical values typically have a mean of 0 and a standard deviation of 1. This means that, while the values aren't strictly bounded, most of them will usually fall between -3 and 3 if the data is normally distributed. If you remember the Gaussian distribution chart we used when discussing outliers, you'll recall that the z-score indicates the relative position of a data point within the distribution. It sets the average value to 0 and uses the standard deviation to measure how far each data point is from the average, with that distance represented as the z-score. So, after z-score normalization, almost all data points are compressed into the range of -3 to +3. Finally, by applying z-score normalization, we've obtained a new dataset. Just like with min-max scaling, we've treated each feature fairly, and you can see that the impact of both height and weight on the data points is now balanced. In this topic, we learned two common methods for data normalization: min-max scaling and z-score normalization. Remember, both of these techniques are very important and widely used, so there are key points for this lesson. When given a simple dataset, you'll need to be able to manually calculate a normalized version of the dataset.